Mhm.
Okay. Hi, everybody. Good morning. Welcome to the Institute seminar. For those of you who don't know me, I'm Ginny Catania, a glaciologist here at the Institute, and I'm so happy to introduce Lizz Ultee, who is our speaker this week. Like all exceptional glaciologists, Lizz got her start in Canada. She went to Queen's, where she got an undergrad in physics and math, and then went on to do a PhD with Jeremy Bassis at the University of Michigan and a postdoc at MIT, and then another one with Alex Robel at Georgia Tech. And she was a professor at Middlebury for a while, and now she's a NASA scientist. And the thing that I love about Lizz's work is it spans so many different areas of glaciology. The thing that I'm really interested in is calving processes. So she looks at the physics of calving, but she also does large ice sheet modeling. And she also looks at glaciers as water resources and tries to understand how to communicate the science that we do to sea level practitioners. So she's kind of across both the science spectrum in glaciology, but also into the social science world of glaciology as well. So I'm really happy that she's here. She's going to be talking about a recent project that she got funded for and some new field work. So it's a little bit more calving focused, but if you wanted to meet with her, I think there's still some time. I'll send out a schedule to talk about all these other projects she's working on as well. So please join me in welcoming Lizz Ultee.
Okay, thanks so much for having me. Thanks, Jenny, for the introduction. I am delighted to be here and to have the opportunity to share some really new stuff, like data I just got 2 weeks ago. So the talk as a whole is also quite new. I will try to restrain myself from just like frantically shouting about data at you. But I hope to save some time for discussion at the end. So, we'll see. We'll see how it goes. I might skip some less interesting stuff. Okay. And here we go. Okay. So the overall plan for our time together, I'll give you a little bit of personal background, although Ginny covered most of it. Some introductory thoughts about why we should bother thinking about ice sheet variability. I'll show you some prior work that I've done about analyzing shorter term and longer term variability separately. And then I will show you some new field observations and finally comment on how we can account for these how we can account for this variability in sea level projections, which is what really motivates this work that I do. So a small amount of personal background. If you don't want to talk to me about science, you can talk to me about any of the things that I mentioned in this personal background minute. I just think ice physics is really cool. Like, look at this puddle that you can stomp on when you're commuting. Isn't that fun? You can shatter some skim ice on your way to work. I have always been very excited by skim ice. I grew up in cold places, and so skim ice and weird curving icicles and all this stuff has been a part of my life for a long time. And you can see all kinds of chaotic ice physics in Greenland too. So I'll talk about chaotic ice physics in Greenland. As Ginny mentioned, my academic background spans more cold places, starting in Canada, doing undergrad research on the GRACE satellite data at the University of Toronto, and studying for my PhD at the University of Michigan, where we have some nice lake ice, Great Lake ice. Isn't that exciting? Now, most of my work is mathematical and statistical methods, and I occasionally go to the ice. So although I will show you some field data today, that's not the majority of things that I do. Let's see if this video will actually work for you. Just remembering GPS. Sorry. So we're recovering GPS stations from the surface of Sermeq Kujalleq, which is the field site that I will share data about today. There are two main motivating questions in my work. The first one is about sea level rise. I'm interested in how much glaciers and ice sheets can contribute to sea level rise in the coming decades. This part of my work involves working on the NASA sea level change team, as well as the ice sheet model intercomparison project. So those are some big community efforts I'm involved in, if you want to chat about those. This on the left-hand side is an animation of a model that I wrote during grad school for the retreat of calving glaciers. And over here on the right is data from Helheim Glacier and our analysis of variability at Helheim Glacier that I'll get into during this talk. The second motivating question of my work is about glacial runoff, wondering where and for how long we can rely on glacial meltwater to protect downstream communities from drought. Because we know that especially in arid mountain regions, glaciers can be seasonally very important to support water resources, which you see on the left, summer contributions of up to 60% from glacier runoff in this particular basin in Chile. And so I'm interested in how runoff coming from changing glaciers affects downstream systems and buffers drought, which is the work that I'm showing there on the right. Okay, so that sums the personal background that you can come and talk to me about if you are not stimulated by anything else in this talk. I would be very happy to talk about these things. But let's get into ice sheet variability as promised, and why we might want to think about ice sheet variability if we're interested in the motivating questions that I shared, namely sea level change. We know that ice sheet mass loss causes global sea level rise. And here is a plot of mass loss from Greenland from 2002 to 2022 during the GRACE missions. And you can see these downward curves of mass change on the left-hand y-axis showing change in the ice sheet in gigatons. The purple one is the sum of those two regions. Oh, sorry. And on the right-hand side, you can see the equivalent sea level change in millimeters. So just over those 20 years, there's been about 14 millimeters of sea level contribution from Greenland alone, which is about a third of the global mean sea level change per year during that time. But you can see that there's also kind of a lot of variability in that, right? There's a seasonal variation. There's also, I would argue, a change in the trend during that time that you see there. So what do we know about this variability, and how can we use our knowledge of variability to better predict sea level change in the future? I'm going to focus on outlet glaciers, which are all the way around the edge of the Greenland ice sheet, controlling the ice flow to the ocean. So this plot is showing you ice flow speed, and where it's showing up bright blue and pink, those are really fast flowing areas that are funneling ice from the interior of the ice sheet out to the ocean. And those outlet glaciers, the rate of their flow is controlling how much ice makes it from that ice sheet interior to the ocean and eventually causing sea level rise. So a lot of what I will show you in this talk is about ice velocity variability, like how does that flow change and what affects that pattern of variability. But we could, of course, also be talking about variability in snowfall, variability in the ocean thermal conditions. Greenland outlet glaciers, like the ones that were highlighted on the previous slide, have been accelerating since the early 2000s. We can see this in a lot of prior work. So here you see plots of two different outlet glaciers, Kangerlussuaq on the top and Helheim on the bottom. Since 1985, the red curve of their speed is like kind of consistent until the early 2000s, and then there's a speed up of both of these glaciers. Their frontal position in blue also retreated during that time, so there's some kind of synchronous variability in certain variables that we're interested in. This acceleration is not only on these two glaciers, but these are two examples for you. And across Greenland, there are many factors that could be driving acceleration, which Ginny has a nice review paper summarizing. So in this schematic of a glacier flowing into the ocean, we see changes from the ice speeding up, we see the ice thinning, we see the front of the ice retreating, and that could be happening as a result of changes in surface mass balance, so how much mass the ice accumulates from snowfall and compaction, changes in the basal conditions, so water at the base of the ice sheet causing it to flow faster or slow down, changes in the ocean, and changes in how ice breaks off at the front and how much iceberg calving we get per year. So if we want to understand and predict variability, it would be nice to be able to tell apart the effects of these different factors and see, is there one that's the most important, or how do these interact on various timescales? We know also that each outlet glacier has a unique setting, and so here are two examples, Umiamako and Sermeq. And you can see that Umiamako is flowing from right to left here in this deep sort of contained fjord, and Sermeq is uncontained and just sort of spilling out into the ocean through a small constriction. And as a result of those unique settings, we see that the response of the ice sheet outlet glacier flow, their velocity response to something like terminus position change there on the top, varies. So these two glaciers have different patterns. They're both retreating, but Umiyamako is speeding up and then slowing down, and Echypsermia is more or less consistently speeding up. So we want to be able to tease apart those effects. There are also different responses to changes in liquid water input. So we think from theory that input of liquid water to the base of the glacier makes ice flow faster. This is suggested to be important in theory, but observations thus far have suggested that marine outlet glaciers, so those calving glaciers that meet the ocean, have a limited role for runoff-driven speed up, perhaps in part because they're interacting with the ocean and there's a stronger driver there, or you just can't see what's going on because of the chaotic front of the glacier. So we have lots of options, and if we want to capture variable mass loss in models, there are lots of things that we might look at to improve our representation of ice sheet variability. So we could try to improve the representation of surface mass balance variability, or iceberg calving, or changes in the ocean, or changes in basal condition. And people work on all of these things, and they're all important. I think it would be nice to be able to see from observations what is like a really high priority for us to work on, or how can we represent these things most effectively for our science question of interest, which for me is multi-decadal to century scale sea level change. This is also important because we know that excluding short-term variability from simulations biases mass loss projections. So if you run an ice sheet model and you don't include short-term variability, you get a different long-term mass loss than if you force it the same way, but with seasonal variability. So here, for example, you can see a 30-year simulation where the colors indicate the same forcing, and the wiggly curves have seasonal variation at the ice front, and the X's are forced with the annual average of the same change. And they end up with different results. So look at the light blue one, for example, on the bottom. The seasonal variation has a different mean from what comes out in that curve of X's, which shows more mass change than the seasonal variation. Unfortunately, you can also get less mass change, like if you look at the dark red curve on the top. The sign of the bias depends on the shape of the glacier bed and also on how big the oscillations are. So it's not trivial to say, okay, well, we can exclude seasonal variability, but then we just correct it by 10%. Which direction should you correct it? This is complicated. So we see this in simulations that are forced with short-term variability, that they come out to a different mean mass change. And we also see if you vary different processes statistically, that the ice sheet tends to drift versus if you force it only with a deterministic forcing. So if you're applying a consistent forcing here over the course of 2,000 years, so a much longer simulation in this case on the right, that mass change is much, much less than if you vary the rate of iceberg calving, for example. So if you have an annual mean that is the same, but you have a larger variability, you have much more mass loss over the course of a longer simulation. So we really want to constrain the types of variability that are important for ice sheet mass change, their time scales of interest, and how we can represent them in models. And I will show you a couple of ideas about how we can get at those things from satellite and field, and a little bit of modeling as well. So the first idea to share with you is that different forcings vary on different timescales. So I showed you that schematic of what could be affecting how glaciers flow. One example is input of liquid runoff, and another example is change at the front, so variation in the terminus position. And if you look at these two time series, their variability looks different by eye, right? So I can look and see that the variation in runoff is strongly seasonal, and the variation in terminus position is kind of seasonal, but it also has a longer term wander. And we can use the variation of these different forcings to tease them apart in satellite analysis. So this is the notion of timescale separation, which I'll show you in a case study at a single glacier. So let's build ourselves a schematic. I've mentioned that there are many factors that could affect ice flow velocity. So if we have like surface velocity here as our variable of interest, this could be affected by atmospheric variability, how much snowfall, how much rain, how warm is it. Could be affected by conditions at the base of the ice, how slippery is it. And it could also be affected by variations in ocean interaction, including things like submarine melt of the ice face, calving events, and whether there is this jumble of ice melange at the front pushing back on the front of the glacier or not. I'm going to lump all of those things into ocean interaction. And these could all operate at different timescales. And indeed, based on the time series that I just showed you, I believe that they do operate at different timescales. And we're going to exploit that fact to look at their correlations with velocity across different timescales. I'm going to show you some data from Helheim Glacier. This is a single large outlet glacier in Greenland. That map there shows you where it is. And this is a picture of the front of Helheim Glacier. All of that jumbled up bright white stuff in the front, that's melange, and that could be pushing back on the face, just in case you haven't seen ice melange before. Wow, ice melange is so cool. Sorry, this is what I told myself I wasn't going to do, right? Okay, so let's look at a case study of Helheim Glacier. We're going to build up our concept map at this time with variables that we can actually take from observations and reanalysis models. We have surface velocity from the NASA Measures program, showing us the flow of Helheim Glacier over several years. We're going to correlate that with surface mass balance, how much mass is being accumulated from the RACMO regional climate reanalysis. We're going to use the same source for runoff, providing liquid water runoff at seasonal scale. And we also have a really dense record of calving front position at this particular glacier. It's very heavily observed. So we have some hand-picked observations of calving front, which sometimes are just a few days apart. It's a really nice record. And you'll notice here that the direction of this arrow over here on the right is two directional. So surface velocity and calving front position, those could be affecting each other, and we want to allow for that in our analysis. Surface velocity is probably not affecting surface mass balance because that's just what's coming from the atmosphere, right? So there's one bidirectional relationship here, and the analysis I'm going to show you allows for that. We have 25 points along the center of flow in Helheim Glacier. So I'm plotting this over its bed topography. And these points that I'm showing you, we're extracting the surface velocity from the satellite observations. And we're going to isolate seasonal and multi-annual timescales in all of these series. We construct smooth velocity series as linear combinations of temporal basis functions. So from our pretty dense but still gappy satellite data, which is the points there extracted at each of these example locations, we construct a smooth series, which is the curve that you see, using combinations of functions that represent long-term trend, a change like a step change, seasonal variability, that kind of thing. So these are composited from multiple types of variability, and then we can isolate them by time scale. At each of the points along our flow line, we compute cross correlations between ice velocity, which you see there on the left, and the three system variables that I told you we were going to investigate. If you yourself are interested in computing some cross correlations, there's a lot of statistical particularities, which I'm happy to discuss offline, but I'm not going to do it right now. So what I'll show you next is the cross correlation produces, this is a cross correlogram, and from this we get two pieces of information. What is a cross correlation? A cross correlation is taking one of these series, like the top purple line, for example, a time series of flow speed, and you slide that time series back and forth along surface mass balance series or the runoff series or the terminus position series, and you see at what time do they correlate most strongly. So you report the strength of the correlation and the time of offset when they correlate the strongest. So I'm going to get both of those pieces of information, the strength of the correlation and when it happens. And I'll annotate for you how to read such a cross-correlogram. We can get the strength of the correlation. Here, the example is about minus 0.2. It exits the significance limits, those dashed lines. And we can also tell that the sign of the lag tells us whether this variable is responding to velocity change, like terminus position could be, or whether velocity is responding to changes in this variable. Okay, so we will look at a single cross-correlogram isolating the seasonal dynamics of this glacier. We see in this example, this is kind of blurry, sorry, that the velocity response to runoff starts upstream and propagates down. How can I tell that? This is a cross-correlogram where each line indicates a location along that central line of the glacier that I showed you before. And we can see that the shortest lags are in yellow, they're upstream, and it propagates down that line until the longest lags between runoff and velocity are in dark purple, so towards the front. So this shows us that the velocity response to runoff is starting upstream and propagates down, which is kind of unsurprising because you are accumulating runoff towards the front. And there could be lubrication upstream, which is kind of pushing ice downstream. So in this example, we see pretty strong correlations with velocity, and the shading there, this is only when there is a statistically significant greater than 95% confidence cross-correlation between this variable and velocity. I will show you the evaluation of all three system variables on a map like that one next. So I'm going to take the cross-correlogram away and just show you the strength of the strongest cross-correlation and when it happens. So here, runoff and terminus position are pretty comparable in cross-correlation strength, which is the shading of that color, up to about plus or minus 0.3 cross-correlation. At most points, they're kind of comparable. Catchment surface mass balance is relatively less important at seasonal scale, which is also not that surprising because the accumulation area is far upstream and it takes a while for changes in surface mass balance to be accumulated by the ice sheet and transmitted downstream. So we see, okay, the strength of the cross-correlation between runoff and terminus position at seasonal scale is comparable. However, what I think is very interesting is that terminus position seems to respond to velocity and not the other way around at this particular glacier. So this here, I've added the time at which that strongest cross-correlation happens. So looking at the lag time, I can see that on the bottom right, which is the lag of terminus position, all of these lags are negative, which means that the change in velocity is happening before the change in terminus position that produces the strongest cross-correlation. So we're able to use this to reinterpret our little schematic that I showed you at the beginning. At seasonal scale, we can see that runoff is important in determining surface velocity, and surface velocity also seems to be important in determining calving front position. The role for surface mass balance is not that strong. So I sort of edited the weight of these arrows to show you the strength of relationships that we see from the data. And if you're interested in this, it's documented in this paper that I wrote with Dennis Felixson, who's a UTIG alum. We analyzed every year in the period 2009 to 2017, and also the period as a whole for seasonal variability. So this is a pretty robust conclusion across the full period and every year within it. If we now move from seasonal dynamics to longer term variability, the multi-annual dynamics, I'll show you a comparable plot of the cross-correlation and lag at every point along the flow line. At multi-annual scale, the terminus forcing seems to be the only thing that matters, which is interesting. So all of these X's mean the correlation is there, but it's not significant beyond the 95% confidence interval. So it's not statistically different from zero correlation. Whereas terminus position, this is the only one that has correlation significantly different from zero. The lag is a little bit harder to interpret at long term because the variability is such long periods that the lags are either simultaneous or it's like 3 to 5 years. Like, what do you do with this? But we see a role for terminus forcing at multi-annual. And so we can edit our conceptual model once again and see that at seasonal scale, we have this forcing of runoff on surface velocity and surface velocity on calving front position. And those relationships are changed at the multi-annual scale. So we have less influence of surface mass balance and runoff on velocity and a stronger influence of the calving front position on the surface velocity. So this shows us this time scale separation that certain forcings are more important at shorter term versus longer term. So here what I've shown you is that we constructed these continuous velocity series that allow us to decompose different timescales of variability based on satellite data. And we found different dominant drivers of velocity variability for this glacier, depending on the timescale of interest. So this might allow us to better inform our simulations if we can force at those timescales of interest, for example. However, I have a big caveat to share with you, which is that this analysis assumed that those drivers don't interact with each other. And actually, we think that they do, which is kind of a bummer. But this allows me to get into my really unhinged excitement phase of the talk. So interaction with the ocean, we think that the interaction with the ocean at big marine terminating glaciers like this might be masking runoff-driven variations. And so these drivers could be interacting and they could also be obscuring each other in the satellite data. So this is my little artificial time series of what you might see as a seasonal cycle driven by runoff in the blue, what you might see as a seasonal cycle driven only by terminus change. And then if you put them together, it just looks kind of like a corrupted terminus driven one. Like you can't really tell them apart. So we would like to know, firstly, if we can tease those apart at big marine terminating glaciers, and what we most need to capture to inform sea level projections. Hooray, I can show you some field data. So I showed you satellite observations, but we need finer scale temporal observations to be able to tell apart things that the satellite might not be capturing because they're happening really fast or interacting at timescales that aren't observed well by satellite. So this is our student Amy, who is valiantly setting up all of the GPS boxes that we deployed on the surface of Sermeq Kujalleq, which is there, also known as Jakobshavn Isbrae. It's Greenland's largest and fastest moving outlet glacier. So you can see the map of Greenland showing you where it is there on the upper left. And here, the background is a map of our field area. This is a long fjord that used to be full of glacier, and now it's not. We have terminus facing cameras on rock, which are facing the front of the glacier and also out into the ice melange. And then you can see some lines there labeled N1 through N4, C1 through C4, and S1 through S4. And at each of those points, we are installing GNSS receivers to watch the ice move, as well as meteorological sensors. And what is happening at this glacier is iceberg calving at the front, and we imagine that we're going to see the effect of iceberg calving first downstream and then upstream, because the ones downstream are the closest to the front. And there's also input of liquid water runoff and possible drainage of these big lakes that you can see in the satellite image, which could be affecting velocity, and we think that it would happen starting upstream and moving downstream. So at this array of field sites, we installed GNSS receivers and MET sensors, which are measuring ice flow speed and direction. And from the meteorological sensors, we also get temperature, incident radiation, and local melt. And we have these time-lapse cameras, which are installed in the location that I indicated. I will now show you some preliminary data, which I've had like, I don't know, 3 days to analyze, but I'm so excited, so I get to share it with you. A major part of this project is actually finding these GPS boxes that have all of our data. They do not transmit. We only know where they are because we know where we put them and we know how fast the ice is moving. And then when we get there, it looks like this. Um, so like, I am just delighted that we got all of them back and that we got data off of them. It's so exciting. And so we have some records that I can show you. We have ice flow and temperature at each of these locations from May through September. So we also have a pretty long field record. We installed them in early May and we picked them up in mid-September. And here, color-coded by line, you can see ice flow speed in the bottom right of each of those points with some sort of slow flow at the beginning before the melt season had really picked up. And then acceleration and some diurnal variability, some spikes, which I'll go into a little bit later. We have local temperature, and we also have a little bit more metadata, but we don't think it's very good. So these are the raw speed records, but now if I show you speed anomaly, which just takes out the mean, we can look more at short-term variability in this record. So this speed anomaly plot shows speed up and slowdown events separated by each of the lines here. So the central line on the top, northern line in the middle, and southern line at the bottom. And we see over the course of the season, several short-term events of speed up where the lines are above zero and slowdown where the lines are below zero, ice moving faster and slower than the mean. And importantly, I'll point out to you that the day of the year 2025 is indicated on the bottom, and these spikes are happening within like 3 to 5 days, which is shorter than the 6-day satellite return time. So these are things that we could not observe with the observations that I showed you previously, which I also feel very satisfied about. It's like, oh, it was worth it. What we can observe from the combination of data is things like the effect of large calving events. So here's data from the time-lapse camera. This is my really crappy hand-drawn ice front in the green. But here on a single day between June 10th and June 11th, the front of the glacier just rips back all of that distance. This is about 5 kilometers across. I would think that that's several hundred several hundred meters of ice, which is missing. And I've indicated large calving events here in these vertical dashed red lines. There's also a really active period, this shaded pink zone, where there's a lot of calving going on. And we can use that qualitative information from the terminus-facing cameras to tell us, okay, when is there something going on that we might want to look at in the GPS data? And if I look at the central line, for example, I'll show you the effect of a single calving event. We can see some calving going on in these dashed red lines, and immediately after the calving, we see a speed up that starts downstream at C1, the dark blue, and propagates upstream towards the light blue, C4. So this, I would argue from my extremely preliminary analysis, is evidence of the ice responding to changes at the front. This is consistent with terminus-driven variability, which I'm indicating to you in these red arrows moving from the front upstream. We also see some interesting events that are unique. So this speed up, for example, is unique to the southern flow line, and you don't see it on the other ones. So is there some interesting dynamic event happening there, which isn't on the other ones? Here, zooming in on that speed up, we can see that it starts upstream, the light S4, and propagates down to the darker S1. So these vertical lines that I'm showing you, this is just the max within this record. You could do much better processing on this to show the propagation of this kinematic wave, but again, preliminary data that I'm psyched about. So here, when we see a speed up that starts upstream and propagates downstream, I think you know where I'm going with this, is consistent with runoff-driven variability. And I'll also point out to you on this nice field map that we see at the right, there are these big superglacial lakes upstream. So there's one dark blue pond there at the head of the arrow and another sort of white scar, which is a previously drained lake. This is just from basic Q Greenland. I did not do anything fancy with this image, but these are persistent lakes which show up year after year. And we could, and indeed, I would say we should, put these together with satellite observations from this season to see when those lakes actually drained, and can we identify the drainage of those lakes and their effect on the velocity of those GPS stations that are sitting just downstream of it. We also know that there's this big trough between the S line and the C line, for example. So it would be unlikely for runoff that affects the southern line to flow under and affect the central or northern line, which could explain why we see those speed ups on certain lines and not on other ones. Okay, so with our field data, we think we can separate runoff-driven and terminus-driven variability, which is exciting. And we still need to do lots of work on this data. For example, we need to produce some variables that we can use for statistical analysis. Everything I just showed you is totally qualitative, me staring at data and telling you that there's stuff there, which is distinct in character, I would argue, from the statistical analysis of Helheim that I showed you earlier. So I would like to be able to do a comparable analysis, but in order to do that, I have to make some time series. Terminus change from the cameras. If anyone is really into processing time-lapse cameras, please let me know, because it seems like I'm going to have to hand pick the front on all of those. We also have local melt from draw wire sensors. And as I mentioned, lake drainage from satellite observations. And I'd like to put all of these into time series that we can use for cross correlations. A cross correlation analysis like the previous one can show us the effect of drivers assumed to be independent. And we're also developing a vector autoregression approach, which is a different statistical method that allows these drivers to interact with each other. So we'll see a little bit more nuanced view. Also, in the longer term, the goal is to unify this field data with satellite data that covers the same period, so that we get certain times of enhanced resolution, but we have a longer term continuous record, so we can tease apart really short term and longer term multi-annual variability. Okay, now that we have spent some time nerding out about variability in satellite and field data, I'll give a little bit of background about how we might account for this in projections. So this is a totally other side of work that I have done. It is difficult to sample variability with the standard methods. So I'll give you a little bit of context. We have a spectrum from simpler to more complex methods of sampling variability. I told you at the beginning that it is important to sample short-term variability because you get a different mean state if you don't. But how should you actually do that? Well, if you have a simple method, then you can run a lot of simulations and sample a variety of parameters or climate scenarios or spectra of internal climate variability. However, often a semi-empirical method like this, these simpler methods assume that the future is going to be similar to the past, and that assumption is becoming less and less good. On the more complex end of the spectrum, we have ice sheet process models, which simulate evolving dynamics. They keep physics consistent between now and the future. We think that assumption is pretty good. But the computational expense of physical simulations limits how much we can do. So we can't sample every part of the spectrum of internal climate variability or of short-term and long-term variability with its own ice sheet model realization, because the expense would be unmanageable. Okay, so I have worked on something which is kind of in the middle of this, called stochastic modeling. We can sample the variability from process models and then use statistical tools to generate many versions of that variability, which we then use to sample lots of future scenarios and test how the variability affects our outcomes. The Stochastic Ice Sheet project is led by Alex Robel at Georgia Tech and involves a lot of collaborators working on stochastic representation of each of these areas of variability that I indicated in the introduction. So we're interested in variation in surface mass balance, variation in the ocean thermal forcing, variation in iceberg calving, and eventually it would be nice to have variation in basal dynamics, but that's a little bit more complicated. So this is a long-term project, which Alex started, I want to say maybe 5 years ago. And the example that I'll show you was something that I worked on during a very short postdoc at Georgia Tech. with stochastic simulation of surface mass balance of the Greenland ice sheet. So the example that I'll show you here is how to generate a representative sample of variability in surface mass balance, and how we train a statistical tool to give us all of these blue lines when we only have a single process model realization, which is the black line. Okay. Oh boy, okay. The format, okay, I'm really sorry. The formatting of PowerPoint might make this a little bit less good. So we're gonna fit a statistical model to the variability of surface mass balance, a variable which is not appearing in this version of the equation, but it's on the left. So surface mass balance will have a statistical model fit to process models. It has a constant term. It has a linear trend. It has a seasonal cycle. It has dependence on past values. Here, this is an autoregression model. And it also has a residual term. We're going to focus our model selection on these components here on the right. You can fit a constant and a linear trend and a seasonal cycle from almost any time series. It's kind of the preliminary work is to remove those things and then focus your statistical analysis on the remaining variability. Okay, so we take these two terms from process models that were included in the Greenland surface mass balance model intercomparison project. These are realizations of 13 different mass balance models, so different ways of simulating processes at the surface of the ice sheet. And what's nice about these is that they all ran a harmonized experiment. So we know that they are directly comparable to each other, and they have all been interpolated onto a common ice sheet mask with 1 kilometer resolution. So we have a very fine data set from which we can take the variability from different process models. We analyzed the 7 models that allowed us to use their previously output data for this purpose. And we aggregate the surface mass balance that they produced to about 200 catchments in Greenland. Let me start by saying we do not want to fit a statistical model to every pixel in our ice sheet model. That does not save us anything in computational expense. So part of the design of methods to account for variability is where can you be clever and save on computational expense in a way that's still going to allow you to run a simulation that means something. So we aggregate to these 200 catchment basins. So here, the one that's shaded blue is shown in the time series on the right. For each of these basins, we have 1 time series for each participating surface mass balance process model. And then we use this series to fit a statistical model that represents its variability. So there are several candidate models that we could use to represent interannual variability. The one that ends up fitting the best is an autoregressive order n model. These are very simple noise models. It just means that the value at the present time depends on noise values from previous times, generally with a pretty short reference time. We also tested some other common statistical models, such as ARIMA, which includes a weighted moving average of several noise terms and a differencing term, and RFEMA, which has fractional differencing that allows for a longer memory. So the ice sheet is a long-term integrator. Maybe we want to represent that. It turns out you don't. It turns out you can just use the super simple AR1 model. And we tell these apart. I'm telling you this in case you yourself want to try something. We tell these apart with the Bayesian information criterion, which is a metric output by stats models, the statistical model fitter, that tells us how good the fit is in comparison to a different statistical model. So the difference in the Bayesian information criterion between the different types of models tells us whether we have a really strong recommendation to use one model over another. And it turns out that we do. We have a really strong recommendation to use really simple noise, which is great. So now that we've fit really simple noise to the blue term, we just have a residual, which encodes our spatial information. And it looks something like this. This is the spatial correlation across basins. So I showed you that we aggregated to 200 catchment basins in Greenland. And we know that surface mass balance variability might be correlated across the ice sheet because it's subject to large-scale atmospheric variability. And the atmosphere does not care where we have put these flow basins. So there's some correlation that we can see that lives in the residual term. If you would like to know more about fitting this model, you can read the paper which describes the method, but I will just summarize for you that we fit this full stochastic model to surface mass balance. And what we gain from the stochastic model is the ability to generate lots of realizations from a relatively contained amount of process information. So for example, we can generate a short period that is consistent with a prior period. Here you see in the blue lines, we only have the process model realization until I think 2015, maybe 2014, because that was the period of the experiment. But with our stochastic generator, we can easily create consistent time series out to 2050, for example, or 2100. And that allows us to use the physics of the process model for a period that it has not been applied to, which is nice. We can also fill the range of observed variability based on just a few projections. So if we have a time period of interest, like let's say we wanted to reproduce 1980 to 2015, we can fill the range of variability and say, oh, well, what could that have looked like in a world that is consistent with that variability? But we only have the one realization of the process model. We have 10 or 100 or 1,000 realizations of the stochastic model. And what can we do with this in the end? We can run large ensemble simulations. So the Greenland ice sheet large ensemble, this paper just came out. We applied this method to surface mass balance, which is in the middle, to ocean thermal forcing on the top, and also to runoff variability. We fit stochastic models to each of these forcings, and we used them to run an ice sheet model, generating 100 realizations of variability for each of our 2 climate scenarios. So we can sample all of that variability until 2200 from just a single realization of our forcing models. And we can see from the models that we've fitted and the ensemble that we've generated that the stochastic ensemble, which is each of these boxes, shows a greater mass loss than the base deterministic simulation, which is the dashed line, in basically every case. So the stochastic ensemble is the box, the median of the stochastic ensemble is a solid line, and the mean is a diamond. And what you can see here is that for the large ensemble, which is the first column, in both climate scenarios, the mean and the median mass loss are below the deterministic simulation. And indeed, for each of several smaller ensembles that we ran to test the effect of covarying variability, only allowing surface mass balance to vary, only allowing the ocean to vary, all of those have greater mass loss than the deterministic simulation. This is an effort focused on the role of internal climate variability in driving Greenland ice sheet change. So this is not like your brand new fresh ice sheet projection that you should run out and use for every application. But we can see the effect of including variability, and that was made much easier by our stochastic method that generates those ensemble forcings directly within stochastic ISSM. Okay, so I have shown you a few looks at ice sheet variability from field data, from satellite data, and also how we can use ice sheet variability in models. I showed you that it's important for multi-decadal sea level projections, something that I care about, to account for ice sheet variability, because you get a different answer if you don't. I showed you that marine terminating glaciers in Greenland, like Helheim, show flow variability at multiple time scales in response to different drivers, and we can tell them apart. I showed you some preliminary field data, which indicates that we can understand dynamics of variability at very short timescales and maybe tell apart the influence of the ice front versus the influence of liquid water runoff. And I also showed you an example of how we use stochastic ensembles to capture variability in future sea level projection. So these are several threads of work that I'm delighted to have the chance to finally bring together. Ginny mentioned that I have wide-ranging interests, which is true, but then sometimes it feels like I just can't really focus on anything because I'm too excited about everything. But having the opportunity to share this with you really helps me draw together for myself also why these threads of work make sense together. They make sense to me anyway. I hope they make sense to you as well. So with that, I thank you for your time, and I'm very happy to answer any questions you might have.
All right, any questions? None?
Great.
Hi.
That was excellent talk. I'm curious, surface mass balance gets used all the time in the modeling world, yet in both your sort of data-driven examples and the stochastic work, it seemed like it wasn't correlating with terminus position or runoff. What can we take away from that? Do we have a problem with using surface mass balance so consistently in all our models as some major driver?
Yeah, so thank you for the question. Should I repeat the question for folks online, or can they hear it? Okay, cool. Yeah, thank you for the question. I think that actually indicates a problem with the length of our observation period. So you mentioned, I'm going to try to navigate back to the slide and we'll see if I'm successful. You mentioned that it looks like surface mass balance is not that important, like in this analysis, which is true, but we only have observations from 2009 to 2017. And the period of surface mass balance variability could be decades, multiple decades, centuries. And it also takes the ice sheet a really long time to aggregate surface mass balance change from hundreds of kilometers upstream and transmit it downstream. So this analysis is, and the field analysis actually, is all really close to the front of outlet glaciers. It's within about 50 kilometers of the front, which means that it's about 250 kilometers from the true accumulation area where surface mass balance is varying and eventually accumulating downstream. So we have a pretty short observational period, which I think is part of why we don't see that much effect of surface mass balance in this area, but also what we see when we run model simulations. Go. So here in the right-hand side, I didn't talk about this, but I'll highlight for you here. There are a couple of small ensembles where we only turned on variability for certain forcings. So the yellow one is where we only have surface mass balance variability and no variability in the ocean or in runoff. And that has the largest ensemble spread, and it's actually the most comparable to the full ensemble. Whereas if you look at the small ensembles that are forced by only ocean variability, like the one in the blue, that has a pretty small ensemble spread. And it isn't representative of a large ensemble at all. So I think at longer term in simulations, the role of surface mass balance is supported by these ensemble analyses. It's hard to see it in observations because the satellite record and the in situ record is really limited.
Oh, and then Ruthie.
Hi, thank you. That was a fantastic talk. I'm probably biased because I'm an oceanographer, right? But your carving front position, that's probably also heavily impacted by ocean temperatures that are in the fjords, right? And I was just wondering, NASA had this OMG mission that I'm not super familiar with, but they did a couple of measurements in fjords for like temperature times. Do you think that is a potential source of data that could go into your stochastic models, or is that just too sparse and too short? Have you any thoughts about this? And also, what would you wish from oceanographic measurements in the future? What would be your dream of data to have as a forcing data set?
Okay, I'll answer the second one first because my wishes are, I think, similar to everyone else's and so pie in the sky. I want data as close to the glacier front as possible, and it's so difficult and dangerous to get there. But maybe if we continue asking narwhals to go there, which people actually do, if you continue, or submersibles, right? If you get data closer to the ice front, that would be really helpful. There is observations of ocean thermal forcing from OMG. I'm not sure how close to the ice front. And the reason that we need it, especially in areas like Sermeq Kujalleq, like if you look at what it looks like in front, like this fjord is full of icebergs almost all the time, icebergs and sea ice. And so the thermal forcing at the fjord mouth is very unsimilar to what the glacier is probably experiencing. And there's been some work also in Sermeq Fjord near Helheim that shows the heat that would be lost to melting icebergs that are already off the glacier. And the thermal forcing that they estimate at the glacier front is really different from the closest possible place to drop a submersible or a CTD. So that's a problem, and I would like to have data closer, but I don't know when we'll get it. That being said, it would be really interesting to try to look at far field data because people have seen longer term, like multi-annual changes at this glacier, Sermeq Kujalleq, based on changes in cool water flux into that bay since 2010, I think. So I haven't analyzed OMG data. That would be a good thing to do. Thank you for the suggestion.
Hi, that was a really excellent talk. Thank you. And I actually, my question was very similar to Sean, so I'm enjoying that similarity about the surface mass balance and how the satellite-based analysis shows that the surface mass balance is less significant on seasonal or multi-annual timescales. And then the stochastic data set forcing the ice sheet model is varying as a surface mass balance on, it seemed like, annual timescales. So if you were to make a recommendation to save computation, at what timescale would you guess that surface mass balance would be impactful? So if you were doing like the very minimal thing that you could do in an ice sheet model, you know, how much would you have to vary that to get something robust?
That is a good question, and I think there's a statistical answer, and I don't know it offhand.
Like 100 years, 10 years?
Oh,
1,000 years.
like, can you use 100-year average for surface mass balance? No.
What about 10?
No, I think you need at least decadal. I mean, I don't think that seasonal surface mass balance variability is that important. This is just my intuition based on statistical analysis I did like 5 years ago, you know. I think annual and interannual might actually be kind of important. And certainly we see that seasonal variability at the terminus is really important. So yeah, the large ensemble that I showed you is annual variability, and you still do see that pretty large ensemble spread. So
Do you think that's a model thing or like a real thing though?
yeah, exactly. I don't know. And it would be nice to be able to say, like, if you wanted to do a glacial interglacial reconstruction, can you just force at 100 years? Wouldn't that be nice? And I don't know the answer. But thank you, and I'm happy to talk about it more later on.
Wonderful talk. I have a question about this within a year variability, and it may just be a timescale resolution thing, like you said. But when you have these GPS observations, I imagine are like every 30 seconds or something incredible, something we could never get from satellites. If you compare that to the lag that you see providing the best correlation in the first part of your talk based on satellites, I mean, here you're resolving velocity response that may be sort of like quasi-instantaneous. At least when I look at those dashed lines, it's sort of, oh, you see a response. But when you look at that on a whole year-long timescale, I think the lags that you were showing were between runoff and velocity. They had some time. They're sort of like weeks to months to maybe a whole season. So what do you think about just and the implications of that for me too is that like maybe that one calving event, there's an instantaneous response, but then also there's like a lagged response that you might observe later. So how do you bring those kind of, or what are your thoughts about the timescale of response that's sort of dominant or the most important to capture?
Yeah, I have not had a chance to do the lag analysis on this data yet. I'll also say that this data is smoothed from what we have. So this is kind of downsampled. We have indeed every 30 seconds observations. There's also like a really chaotic one that's just all over the place. And I would like to imagine for myself that that's because it's in a heavily crevassed area that's sort of jumbled around all the time, but it's not, it's just bad data. So I think that the runoff example in particular, you see what I would interpret as changes in the seasonal drainage system. So we think from theory that you have a runoff input which accumulates over the melt season, you get more and more runoff coming in, but the velocity change with that seasonal runoff is not directly correlated because at some point the subglacial system changes, becomes more efficient, and then even though you have lots of runoff, it's not lubricating the base as much. So that's kind of a nonlinearity, which is accounted for in physical process models that we are not going to see here. Here in short-term data like this, we're really only going to see kinematic waves, I think. So something happens and it propagates up glacier because the glacier is a soft solid that kind of propagates signals up and downstream. I like this data because I'm a nerd and I think it's really interesting. I'm not going to use this to directly force an ice sheet model because that's absurd. But we do have a modeling component of this project where we're interested in what dynamics that we can observe might be reproducible in an ice sheet model that we force at like hourly scale. So okay, you asked what might be most important to capture in an ice sheet model. And I think it really depends on your motivating question. And I am always coming with the motivating question of how can we improve multi-decadal sea level projections, and why multi-decadal? Because it's what people will use for infrastructure. Like, so boring. But like, if you're interested in millennial change, obviously you're not interested in this. But if you're interested in fisheries or in tourism, like someone who lives in Ilulissat might be, they're probably interested in the short-term stuff for sure. It depends.
Sign up to meet with her. There's also, where's Michaela? There's a lunch happening as well. Are there any spots available? Maybe, yeah, that could happen as well. But please join me in thanking Liz for her awesome talk.
I am not sure I totally understand this fantastic stuff, but like